Hello, and welcome to our next set of notes. We're doing section C today, 6C. We're going to talk about the normal distributions, some of the things like standard scores. So the normal distribution is a specific type of spread of data set. It's going to be symmetric, unimodal, and it's going to have kind of a bell shape to the distribution. These are nice distributions to work with. Statisticians would love to be working with these kind of data all the time. There are things they try and do to get to work with these specific sets of data. So the nice thing about these is if you know their mean, their center, and you know their standard deviation, the spread, then you basically know everything you know about the data set and can give a lot of information about that from just those two values. So these would be two, normal distributions. Again, they're both symmetric. You can see where the mean is in the middle. They're spread out evenly. Unimodal, there's only one bump. There's not going to be multimodal or bimodal here. And they have this kind of nice bell shape. You can see at the ends, they kind of go off to fit, forever on the ends on both of these. The values are most common in the middle, and then they kind of spread out. They kind of get less common, spread out on both sides. It's a nice even spread. So like we would say this one's a uniform, normal distribution. And this one, because it's right skewed, it's not symmetric, would be not. So this would be our normal distribution. And this one is skewed, it's not symmetric. So it's not normal. So we prefer, if you're a statistician, you hope to work with that set that looks like this, normal, versus this. And there's ways to kind of get to that, techniques and stuff like that. We're not going to worry about too much. We'll leave that to the statisticians, but a lot of times that's something they want to work with is with these nice normal distributions. Now, what leads to a normal distribution? A normal distribution, most of the data is going to be close to the mean. So most results are going to be kind of close to average. You're not going to have a lot of values that are really far from average. So most data is close to the mean. That's kind of what gives it this nice unimodal shape. Data is spread out evenly for a symmetric distribution. So it's spread out evenly, means there's not like one side where it drops off fast for some reason. We talked previously about how the right skewed, left skewed, how that occurs. That's not going to happen here. You're going to have just a symmetric set of data. Values that are far from the mean are going to be increasingly rare. So the further you get from what's typical average, the less likely those values are. So values far from the mean are increasingly rare. And then values that result, the values will result from a combination of many different factors. So there's lots of different things that cause the data result that you get, when you're doing your study survey. But there's lots of little different things that can, are factors in that. Then those are going to be what cause you to have this kind of nice normal distribution. So values result from many different factors. So let's look at a couple of different ideas and try to decide if this would be a nice normal distribution. First one is wages at a fast food restaurant. And this one we say probably not, because with this, you're not going to have this nice symmetry. So, symmetry is needed to have this. And symmetry is when things are spread out evenly. But fast food restaurants usually are kind of right skewed. They kind of look like this because you have like minimum wage. You have your peak, which is usually a little bit above minimum wage because, not everybody starts maybe close to minimum wage, but some people work there a little bit of time. They have a shift differential if they work like later in the evenings or something. You might have gotten a little bit higher management, shift manager type stuff. You have your people that make even more money because they've been there a long time, or they're like store managers and might manage a couple stores or stuff like that. But yeah, so we'd say this one is not going to be symmetric, and so it's not going to be uniform. This one would not. You would not expect to be uniform. Now, gas mileage of your car would probably be a good example of something that would be uniform. Most of the data is going to be close to average, so most of the time you're looking at the average mileage per gallon for your car. It's going to be spread out pretty evenly. Some days you're going to have mileage that's a little bit better, some days it's a little bit worse, so it's going to be kind of spread out evenly. There's not one reason why one's going to be way higher than the other. Values that are far from the mean are going to be really rare or more rare. You're not going to have super great gas mileage all the time. It can happen, but it's going to be rare. And the higher that, the better it is, the less likely it's going to be to happen. And the values result from lots of different factors. There's things like wind direction, how clean the roads are, how many people are in your car, how much weight you have in the trunk, how many stoplights you hit. Like all those things could affect your mileage. So many different factors. It's going to be nicely symmetric. There's no reason, I think, for this one to be not uniform. So we'd say this one is going to be uniform. We would have a nice, bell shape for this. In the middle would be your average miles per gallon, but you're gonna have sometimes better, sometimes worse. Gross income of 18 to 24-year-olds in Denver, Colorado. I think I'd argue that this one's probably not going to be unimodal. This is probably bimodal. Because if you look at the 18 to 24-year-olds, you're including the people that are like still in school, like maybe going to college and stuff, who maybe aren't making as much money because they're doing college full time, versus people that might go into a trade right away where they only need a year or two of school and they're already making full-time wages. They might be making a lot more. So I think you might have like part-time or students versus the college grads, because some people are going to be done before they hit 24. So you got some 23, 24-year-olds that are going to be working full-time with a college degree. And then your full-time workers, people that maybe they didn't even get a college degree, but they got a job where they're working full-time. In a year or two, they might be even working their way up the ranks if they're good at what they're doing. So probably bimodal, which means it's not uniform, because if it's bimodal, it's not going to be uniform. So uniform data, is what we're looking for. Normal. I keep saying uniform. It helps if you say the right word. I am the worst about trying to say, uniform instead of normal. Normal. Uniform is different. That's flat. This is supposed to be normal. I did it the whole time. I'm sorry about that. All right. So, again, normal data is going to be this nice bell-shaped curve, symmetric, unimodal. That's a normal distribution. That's going to happen. There's lots of different factors. There's not two distinct groups, which would make it bimodal. There's not lots of values far away from the mean. Most of it is going to be close to average. That's going to be what gives us this normal distribution. Now, we said if you have a normal distribution and you know stuff about standard deviation, that's really powerful. One of the reasons is because of this, what we're going to call the 68, 95, 99.7 rule. So, since normal distributions have this nice bell shape, you can describe them just knowing their standard deviation. Standard deviation gives the average spread of the data around the mean. So if you know the mean and standard deviation, that's really all you need. We can use this to give some precise guidelines for the percentages of the data. So what happens is if you have this nice normal bell curve shape, and you know where your mean is in the middle, then you can say that if you go out one standard deviation, so one standard deviation up, one standard deviation down, go out one standard deviation from the mean, so you spread out one standard deviation, you will get 68% of the data. That's more than 2/3 of the data. So more than 2/3 of the data, 68%, will lie within just one standard deviation of the mean. If your mean was, say, 50, your standard deviation was 5, that means that between like 45 and 55, because you go 50 up 5 and go down 5, between 45 and 55, 60% of the data will fall in that range. If you go out 2 standard deviations, then you count your standard deviation twice. You go out up 2 and down 2. Then you get 95% of the data. We mentioned that last time we talked about standard deviation. We said that most of your data is going to lie within 2 standard deviations, and that's what we're saying. We're saying 95% of your data is going to be within 2 standard deviations. So that catches almost all your data. If you go out 3 standard deviations, you don't quite catch everything still. There's still some data values that might be outside there, depending on your data set. But you're going to catch 99.7%, which is almost everything. There's just 0.3% that's left over after you go up 3 standard deviations. Most of your data is going to be within 3 standard deviations, 99%. So for example, using this 68, 95, 90.7 rule, which is on the formula sheet, so basically this right here, this is on the formula sheet, say what happens if someone has an exam where there's a mean of 45, and a standard deviation of 10. Well, this tells us first that if we take that 45, we go up and down standard deviation of 10. So we add 10, we get 55. Take 45, subtract, we get 35. So between 35 and 55 is 68% of our data. So 2/3 of the results are going to lie within that range. You know, the majority of the people taking this test are going to get a score somewhere between 35 and 55. That's what that says. It also says that between 25 and 65, so now I'm going up 2 standard deviations. So if I add 10 twice to 45, so I go add 10, you get 55, add 10 more, you get 65. Or I get down 2 times, so I go 45 minus 10 and minus 10, I get 25. If I go between those two numbers, then it's 95% of the data. So the vast majority, almost everything, like 95%, it's not quite everything, there's still 5% left, but it's pretty close. This is like 19 out of 20 is going to be in this range. So the vast majority of people are going to be between 25 and 65 on this test. So someone that's got a score that's below 25 or above 65 is pretty rare, unexpected. If I just picked a student at random, I expect their score to be somewhere in that range. If I go out 10 more points, so I do the standard deviation one more time. Each time I'm going out the standard deviation. So I go up 10 more, so I get to 75. I go down 10 more, I get down to 15. If I go from 15 to 75, this is going to include 99.7% of the data. That's almost all the data, right? 99.7, and that's only like 0.3%. If you had 100 values, you would not even have a whole, you'd have like one data value. I mean, out of 200, it'd be like one data value still. There's not very much out of that data set that would be outside, just like 1 or 2 values. Most of it, almost all of it's going to be within that range between 15 and 75. So if someone takes this test and they get like an 85 on this test, I would start looking to see if maybe they cheated, because they are the really rare, unusual score. The score should probably be between 15 and 75. Anybody who gets outside of that, something's going on. That's kind of weird. So that's the 68, 95, 99.7 rule. Another name for this is called the empirical rule. That's just another name for it. It's just it's a general rule of thumb for the standard deviations that we can kind of say, okay, well, if we go out this many standard deviations, that's what percent of the data we have. And we use this in real life because sometimes we want to know what percent of the values are within a certain range, so we know what to expect, that kind of thing. So let's actually do this. We're going to use it. Now, it gets a little more complicated because we're not always looking for out 1 standard deviation both sides or out 2 standard deviations both sides. Sometimes we want to know just one side. Sometimes we want to know between 2 certain values. So we're going to do this. I'm going to do a couple where we'll find we'll have the mean and the median, and we use the 68, 95, 99.7 rule, and we'll figure out what percentage falls in that area. So I got 3 parts. I got this little graph drawn 3 times. And first off, they tell us the information. They tell us that the mean is 70. You'll see sometimes this symbol right here. This is mu. It's just a symbol that statisticians use for mean. It is a Greek letter, mu. And then sometimes you'll see this symbol here. This is sigma, and that is a Greek letter for standard deviation. So this one's our standard deviation, sigma. This one's mean score, this is mu. So they just gave us that information. Now, using that information, we know that the mean goes in the middle, right? That's where the mean goes on our data set. So we're going to put the 70 in the middle. And then the 1, 2, 3 just tell us how many standard deviations we go. So the first standard deviation, we're going to add 10, so that'd be 80. The next one, we're going to add 10 more, so that'd be 90. The next one, we're going to add 10 more, we're going to go 100. So 100 would be out like 3 standard deviations. If we go down, you say 70, subtract 10, we have 60. Subtract 10 more, we got 50. Subtract 10 more, we got 40. So 3 standard deviations is going to be between like 40 and 100. 2 standard deviations would be 50 and 90. And then 1 standard deviation would be 60 to 80. And then 70 is the middle of the mean. They want to know what percent scored above an 80. So think about this chart. I'm actually looking for the range. So I'm looking for from 80 to the right. I'm looking for this part. Now, a couple things to note. This is a symmetric graph, and 0 is the middle, which means that this side right here, that's 50% of the data. And this side over here, this is 50% of data. They're also nicely symmetric, so the 2 sides match. I need to find this piece, though. That's what I'm looking for. I'm looking for this piece, because above an 80 is going to be that piece. Now, I got to figure out how to get this piece. So there's a couple ways to do it. I think the easiest way to do this is actually to think about this piece first. We know that this piece right here is going to be 68%. because that's one standard deviation. So you go out one standard deviation on both sides. That's that middle part of the last page, right? That's 68%. You go out that one on each side, that's 68%. That's 68% right there. But if we take this and cut it in half, divide it by 2, because these are equally matched pieces, so we divide by 2, we get 32% is this region. So this region right here, this is 32%. Now why do I want this region? Well, if I have this region right here, the 32%, I could take this whole side, which is 50%, subtract 32%, and what's left is everything else. So I'm going to do 50% minus the 32%, and here I'm going to get 18% for this region. This region is actually 18% right here. So use the fact that half of this chart is 50%. Use the fact that half of 68% is 32%. And we subtracted 32 from 50 to get this 18%. So that's one way you could do this. Sometimes when you need a piece like this, you might think about how can I remove the part that I don't want and then use the rest. This 50% as half is very valuable because I can just kind of think about one side of the chart at once. I don't need to worry about the whole thing. I didn't need to find just this piece, and I didn't have a better way of doing that than just saying, well, 68 is the whole thing right here. Half of that's 32. And again, that's the nice thing about the symmetry, is so everything you can cut it in half. I can take 68, cut it in half and get one side. I can get 95 and cut it in half and get one side. I can 99.7, I can cut it in half and get this side. Notice, and then this stops at 3. I get a lot of times students think that 99.7 goes forever, but it doesn't. It stops at 3. There is actually a little bit of value at the tails. That's why if you took half of 99.7, you wouldn't get all 50% on this one side. You'd just get up to here. There'd be a little bit left over at the end. It's like 0.15. Okay, let's try it over. Let's do below 50. So we're going to do below 50. So this time I'm looking at below 50. Well, I need to label this again. Remember, 70 is the mean. That was the mean they gave us. We got 60, we got 50, we got 40. Well, we want below 50. So we're looking at just from here on. It's going on forever. Looking at this tail, that's the piece we want. Now this time, I'm going to still use that 50 trick. I'm going to look at this half, but I want to take away this piece that we don't want. So I'm looking for this piece right here. The trick on doing this one is thinking about now I'm going out 2 standard deviations. So I'm going to go out 2, 1, 2. If I went out 2 on both sides, 2 on both sides would be 95%. That's from here to here. That's 2 on both sides over here. I don't want both sides. I just want one side. So I'm going to do that trick again. I'm going to take 95 and divide by 2. What do you get? 47.5? It's 47.5. I'm doing the math right. So that 47.5% is this side. This is 47.5%. Now what I can do is I can remember that this whole side is 50 for this half. This whole side is 50. So if I take the 50% of that whole side, subtract the 47% that's right here. It seems crazy that so much, but remember the middle is where most of the data is, right by the peak. This is most of the data. These tails are going to be pretty small. So that makes sense that most of the data is going to be in this middle range. I subtract that 47.5%. What's left will just be this tail. So 50 minus 47.5 gives me 2.5%. And that is our answer. This little tail is only going to have 2.5% of the data because it's just this end. So again, I looked at 95% because that's going out 2 standard deviations. So cut that in half to get 47.5, which is just this piece here that I don't want. I'm going to find the piece I wanted to get rid of because I know this whole side's 50. If I get rid of this piece I don't want, I'm left with the piece I do want, which is 2.5%. Now, one more thing you might do is you actually want to find the value between 2 ends. So I'm going between 60 and 90. So if I label this with my 70, 80, 90, 100, 60, 50, 40, I label it like that, and I say I want to go between 60 and 90. So I want this region. If I want this region, you'll notice it's not quite 1 standard deviation because this one goes up to 2. It's not 2 standard deviations because that goes out, so not so good. So I actually need to find this a little differently. There's a couple ways to do this. I think one way to do it is actually to take and find this region and remove that, because if I take that out of a 95, I'll be left with this. So I'm going to find how much this region is first. Now to find this region, I can think about how normally I would do, 90, so this is kind of like having a whole 95, but I don't want this middle piece here. I don't want the 68 part. And again, this is actually only one side of it. So what I can do is I can take this side that, is my half on this side. That's my half. And I think about how this piece is half of 68. So I'm going to do 68 divided by 2. And this piece would be 95 minus that 34 right here. So this piece right here is just 34%. So if I could find this piece, I can take away that piece from it, from this whole side, from this whole piece. I take away 34, I'm left with this piece. So I'm going to figure out, okay, well, here's out 2 standard deviations, so that's 95. But I only need one side, so I'm going to divide by 2. So that's going to be 47.5 again. But I'm going to take 47.5 minus 34 to get this piece. So here I subtract that and I get 13.5. So this piece is 13.5. So I found this piece. Now, if I think about how this whole thing right here, from here to here, maybe I'll do it in a different color. Let's say this whole piece from here to here would be 95%. And I take away this piece, what I'm left with is the piece I want. So I'm going to take 95, subtract this 13.5, and that'll give me just the blue piece left that I want here. So this would be, I don't know, 12, it's 11, 90, 80. 9 minus 1 is 8, 80. 5 minus 3 would be 2, but I have to subtract a little more, so 81.5%. And that would be this region I'm looking for. So 81.5 is this whole region. This whole thing right here is 81.5%. Here to here. That's 81.5%. We found it one way. I probably could have done it different ways. There's more than one way to do these all the time. I did it by finding out what this piece was first. Taking those 68 95s, cutting them in half so I can get just one side. The half of 95, which is 47.5, minus the half of 68, which is 34. Subtracting those gave me this difference, gave me this space in the middle, and I can subtract that from 95 to get just this piece. But there's definitely more than one way to do it. I could have found half of 95 and then half of 68 is 34, and maybe added those up. Probably the faster way. There's more than one way to do them all, so it's kind of just which way works for you. But you really have to come into using the halves. Think about what half a side is, like 50%, and then using that 99.7, 95, 68, and then doing it that way. So that's using that. But again, we're able to look at something like just having the mean and the median, the standard deviation. They have the mean and standard deviation, and knowing it's a normal distribution. Then you can sit there and say, what percentages are in these different ranges. We found the percentage of values within that range. So out of those 1,000 students, I know that like 81.5% of them are going to have some score between a 60 and a 90. There's only going to be a few that are below that and a few above. There's still people up here and down here, but I found the percentage within that range. Okay. Standard scores, or the Z-scores. So a lot of times we want to know the distance of a certain value from the mean. We did the standard deviations where we're finding the distance, the average distance for all the values. But a lot of times we want to look at a value and say how far on average is that from the mean in terms of standard deviation. This is what you do anytime if you have a kid like I do, and you take them to the doctor, and they do head measurements or weight measurements or height measurements, and they say they're the such and such a percentile. what they're doing is they're looking at what's average for a kid at their age range, and then comparing them to that average. There's finding out how different they are, and they're looking at like are they above or below. That's kind of this kind of thing. So z-scores, standard scores, it's a way to measure how far someone value is from the mean. So to calculate z-scores, this formula is on the formula sheet. You take your value from your data set, the one you're looking at, subtract the mean, so that gives you actual distance from the value to the mean, and then you divide it by standard deviations. So then you get the distance in terms of how many standard deviations. So for example, we have a data set with a mean of 100 and a standard deviation of 10. We've been using 10 a lot because it's a nice round number, but on the homework it won't be always like 10. The value 125 has a z-score of 2.5 because 125 is above the mean by 2.5 standard deviations. Because if you do 2.5 times 10, so 2.5 times 10, you get 25, which is how much 125 is above 100. So it's 2.5 or 2.5 standard deviations from the mean. So that standard deviation, the z-score, 2.5, is telling you how many of these standard deviations away. Remember we said most values are within 2 standard deviations? So something like 2.5 away from the mean is actually kind of unusual. We'll say this is a pretty high score. It's going to be kind of the genius kid in the class because they got 2.5 standard deviations above the average score. That's what that means. A couple facts about the standard score you should know. First off, the standard score of the mean is always 0 because it's a measure of how far you are from the mean, and mean minus mean is going to be 0. So if you look at the mean, it's always going to have a z-score of 0. Standard scores or z-scores above the mean are always going to be positive. So this person that's 125 score was above average, so they end up with a positive 2.5. So anything above average is going to be positive. Anything below average, below the mean, that's going to be negative. So if someone had 25 points below 100, so they're like 75, they would get a negative 2.5 because that would show that they're below. And that's what you would say, okay, well now that person's really far below average. This would be unusually low score. Standard score is usually, kind of say almost always, between -3 and 3. We said that like 99.7% of the data is between 3 and -3. So the standard score is almost always between -3 and 3. If you are doing any of the homework, quizzes, tests, and you get a z-score that's beyond 3 or -3, so you get like 4 or -4 or something like that, that's a good time to go back and double check and make sure you did it right. You might have a mistake because we don't expect the standard scores of z-scores to be beyond 3 or -3. That's usually within those values. They can be positive, they can be negative, it depends if they're above or below average. They should be less than 3 or not as far as like -3. Let's do another example. This one, we have the mean is 100, so that's our average. Standard deviation is 15 this time. I changed it up. And then we're going to find the z-scores for these scores right here. So we're going to find them for 85, 100, and 127. So first off, find the z-score for 85. So our value is 85. That's our data value. So we take the data value, we subtract the mean. So we're going to take the data value, 85, and we're going to subtract 100, because that's the mean. And then we divide it by the standard deviation. So this is the formula we're using to find the z-score. Data value minus mean over standard deviation. So 85 minus 100 over 15, because that's our standard deviation. And that's going to give us our z-score. Well, in this case, 85 minus 100 is -15. Negative 15 divided by 15, we actually get -1. And it makes sense, because if you think about it, 85 is 15 below 100. So it is 1 standard deviation below 100. It's negative because it's below. That's what the negative is telling us. So this person scored below average. Or 1 z scored below average, 1 standard deviation below average. They're still in that middle 68%. So they're within like the the middle range for 68% people. We're between like 15 below and 15 above. But they are on the lower end. They're below average. Let's do the next one. So I'll do z-score with 100. So my 100 is this value. Subtract the mean, which is also 100, divided by 15. But of course, when you do 100 minus 100, you get 0. And this is what I was talking about. Anytime you do the z-score for the mean, the answer is just going to be 0, because 0 divided by anything is 0. So I don't even need to do the math, really. You look at this and say, oh, well, that matches your mean. Anytime you want to find the z-score of the mean, the answer is 0, because the mean is not any distance away from itself, right? 100 is the same value as 100, and z-score is a measure of distance. So how far is the mean from the mean? Well, 0. It's not any far from the mean. So the z-score of mean average is always 0. last one, we're going to do z-score of 127. I had to throw 1 in here that wasn't a nice whole number, so 127 we'll find out we get at least a decimal. That's pretty common with z-scores. Okay, subtract 127 minus 100 by 15. So 127 minus 100 is actually 27, so we get 27 over 15. This is going to be positive, right? Because 127 is above average. It's over 100, so we're expecting a positive. Just got to figure out what it is. So we take 27, 7 divided by 15, and we get 1.8. So 1.8 is the z-score. So this score is above average. In fact, it's significantly above average. It's 1.8 z-scores or standard deviations. That's 1.8 standard deviations above average. It's not quite to the 2, where it's like the very top of this like middle couple range, but it's still pretty high. Like this person's doing really well. They're way above average. Again, if you get a number and you're doing z-score like this, and you get like beyond 3 or -3, that's really weird, and you kind of go back and double check it. That's where you want to make sure it's not messed up. Most of these scores are going to be between 2 and -2 most of the time. Some will be between -3 and 3. Anything beyond 3 or -3 is just really peculiar. Okay. Now, there's a relationship, pretty tight connection between z-scores and percentiles. So percentile, it's basically a percentage, but it's a percentage below. So the percentile of a data value is the percentage of values in the data set that are less than or equal to. So percentile is the percentage of values that are less than or equal to that data value. So when I talked about, taking my kid to the doctor and they tell you, okay, his height is in the 80th percentile, what they're saying is that their height is as high as or taller than 80% of other kids their age. That's what they say. Or if they say, your kid's weight is in the 40th percentile, that means that their weight is only higher than 40% of kids. That means the other 60% of kids are above them in weight. If your kid's at 50th percentile, that means they're exactly average. So if you go to the doctor and they say, your kid's brain, head circumference is 50th percentile, that means that their head circumference is perfectly average. It's not above average, not below average, it's average. So percentile is the percent of values with that or less. If you take a standardized test and you get 80th percentile, it means you beat 80% of people taking that test, which is awesome. Yeah, you beat 80% of people. There's still 20% that beat you, so you're not at the very top, but you beat 80%. I do give you this chart, so this will be on the formula sheet. This chart just takes the z-scores and gives you the percentiles that go with them. For example, if you get a z-score of 0, remember that means you're the mean, you're average, your percentile will be 50% because you beat 50% of people. If you get a negative percentile, is negative z-score, any negative z-score you'll notice will always have a percentile less than 50 because you're going to be beating less than half the people. 0 is half, but negative is going to be less than half. When you get into the positive z-scores, you're going to have more than 50 because now you're beating more than 50% of people, more than half the people you got a score better. So then we did that like 1.8 z-score we just calculated on the last page. They were in the 96th percentile. So they had got a score that was above that of 96% of the students. So if 100 students took that test, they only had 4 of the students that beat them. They beat the other 96. So that's what that means. So z-scores correlate to these percentiles. And again, so you can, anytime you have a z-score, you can look up its percentile and find out what percentage of values are below that number. So here I gave you a couple percentiles, we're just going to look them up. So the first one is 0.75. So 0.75 as a z-score. It's up here, here's 0.75. It's going to give us 77th percentile. So 77.34%. That tells us that there's 77% of students of scores are below this score. We don't know what the score is, we just know it's a z-score. But 77% are below that. If I had negative 1.2, so negative 1.2 right there, I would go over here to negative 1.2 and look up the percentile. Because it's below average, and it's actually pretty far below average, right? Negative 1.2, it's not negative, decimals, it's negative 1.2. Only 11% are going to be lower than that. So it's going to be lower than most of the scores. So this one I have 11.51 as its percentile. That's the percent of values below or matching that one. If I did 2.17, notice this one, there's not a perfect match. So I got 2.1, I got 2.2. So it's actually kind of in the middle here. What I would do is I would look for the best approximation. The number closest to 2.17 is actually about 2.2. So 2.2 is the closest because 17, is closer to 20 than it is to 10. 7 is big, so it makes the 1 go up. So 2.2 would be actually the closest, and that's what we'd use. We'd actually use 2.2, not 2.1, because that's the closest value. So a lot of times that happens because this chart doesn't have all possible numbers on it. It's a small chart because we're not getting too super into it. In my stats class, we'd find calculator ways to get the exact numbers, but we're not worried about that for this class. We're going to keep it easy. And so we'll just say, 2.17, just round it to 2.2, use that number, and that number gave us this 98.61 percentile. So this 2.17 is close to being a 98th percentile, 98th percentile. In fact, it's somewhere between 98.2 and 98.6. So that's what that is somewhere between those two. So we'll just use the 98.6, we'll just use the closest z-score, which will give us that one. Okay, one more thing you can do. So far, we've been finding these z-scores, and then now we saw how you can take a z-score and find the percentile. Last thing is you can actually kind of go backwards. Not backwards. I forgot. I'm doing it wrong. So now we're going to actually find the percentile, starting not with the z-score, but starting out with the actual data. So here's the data set. So they say this time we're dealing with cholesterol levels in 18 to 24 years of age, normally distributed with a mean of 178, standard deviation of 41. So they give us the mean, they give us the standard deviation, and they ask what percentile. So asking a percentile, he say, 20-year-old man, so he fits in this group, but his cholesterol level is 195. So they want the percentile, but before we can get a percentile, we need a z-score. So the trick here is find the z-score first. So before I do anything else, I'm going to use that z-score calculation where I do z is the value minus the mean with standard deviation. In this case, the value they gave us is 195. That's his cholesterol level. We're going to subtract the mean, which is 178. Now we're going to divide it by the standard deviation, which is the 41. So it's finding a z-score, like we did just 2 pages ago, not a big deal. So we're just going to find the z-score. So 195. You do have to be careful when you're typing this in. I get students that try and type this all in one step, and they do it like this. And it doesn't work because your calculator knows order of operations. It's going to do division before subtraction. You'll see me, I just usually just type it in separately. So I just type the division, subtraction, and then hit divide by 41. And that way it works. The other way to make it work is you could just put a parentheses around the top. And that would work in the calculator. So if I do parentheses, 195 minus 178, close that, divide by 41, that would work and give you the same answer. So if you want to use parentheses, that's fine. You can just do it like me, where you start subtraction and then just type division. But you gotta be careful not to forget that parentheses. Okay, so I get 0.41. I'm probably not going to do much more than 41 because you'll notice on my chart, it's mostly just 2 decimals or maybe 1 decimal. So I'm not going to go any further because I'm not going to help with my chart. So I'll do 0.41. The 4 would just leave alone. It's not enough to make it round up, so I'm going to do 0.41. Even 0.41 is actually not on my chart, right? So 0.40 and 0.045. But I'll go with the closest one. In this case, that's 0.40. So I'm going to go with this 0.40 and see if the percentile is 65.54. So I was looking for the percentile. Once I have the z-score, then I'll use the chart. With z, in this case, I'm actually going to use 0.40. That's close to 0.40. That's about 0.40. It's closer to 0.40 than 0.45. And that told me that for 0.40, I got 65.54%. That's your percentile. So we knew his cholesterol level. We knew the average cholesterol for the men. We knew the standard deviation. And we took his cholesterol. We found his z-score. He's 0.4, which means a little bit above average. It's positive, so it's above average. And we turned that into a percentile. So now we can say he's got higher cholesterol than 65% of the men. And that's what we can tell him. Say, okay, you're in the 65th percentile. That means you have higher cholesterol than 65% of men. The other 35% are above you, so you're not in the worst situation, but you might think about lowering a little bit to get closer to the average, because you are a little high. It's higher than average. Now let's do the next one. So the idea again, they want to find the percent. This one they want what percent of men have a cholesterol at or below 178. So I really want to find the percentile for 178 is what we're doing here. So we're looking for another percentile, because at or below, that's the percentile for 178. So in this case, I do the same thing. I find the z-score first. 178 is going to be the value. The mean is 178, and standard deviation is 41, but you guys hopefully already know what the answer is, because if I do 178 minus 178, I get 0, 41, or I get 0. Because this is the mean, right? Anytime you use the mean, the actual average, then the z-score is 0, and the percentile is going to be 50%, right? Because we said previously, z-score of 0 means your average, which means you beat exactly 50% of people, because averages means you're in the middle, 50% below. So z equals 0, we'll go and say, okay, from the chart, that is the 50th percentile. That's what it means to be average. You're higher than 50% of men, but you're lower than 50%. That's what it means. So this person has higher cholesterol than 50% of men. The last one. This one's a little tricky because this one says over 200. You gotta be careful here because we don't want the percent below now. We don't want the percentile. We actually want the percentage above. So we'll be careful about that. We'll get to that. First off, let's find his value. So find the z-score. We're going to take that 200. Again, we're going to subtract the mean, which is 178. We're going to divide by standard deviation, which is 41. Now I give us our z-score. So again, I'm going to type it in. If you want to do it with parentheses, I'd do parentheses 200 minus 178. Close that parentheses. Divide by 41. That's how you do it with parentheses. You like that. Because I'm above average, 200 here is above average, I expect a number above average, so 0.54, I guess it would be rounding to. So 0.54 is above average, right, because it's positive. We're looking at z-scores that are positive are always above average. That would be what we use to find their percentile from the chart. But the problem is 0.54 is not on the chart, right? We have 0.50, we have 0.55, we have 0.54. So I look what we're closer to. And 0.54 is a little bit closer to 0.55 than it is 0.50. So we're going to say this is about, it's not exactly, but it's closer to 0.55 than it is 0.50. And so using that fact, we'll go to 0.55 and say he has 70.88 for the percentile. So 70.88 is the percentile. So the percentile equals 70.88. Remember, this is the percent below. We want the percent over 200. So anytime we want to go above, you don't want to go below. Well, you're still going to use the percentile chart to get your percentile. We have one more step. You're going to take 100, which is everybody, subtract the percent below, and your answer, what you have left, in this case it's like 29.12. That is the percent above. If you have 40% below, you're going to have 60% above. If you have 70% below, you're going to have about 30% above. So it's close to 30%. That's what that is. So be careful. Whenever someone says over or above, that's when you have to do subtraction. The semester project that you're going to be doing for statistics, we're going to be doing a statistical study of M&Ms. You will have possibly this situation where you're trying to find a percentile. And if you need to find percent below, you just do that, you're done. But if you need to find percent above, then you have to do the subtraction. Because again, you always find percentile from the chart, and then you subtract to get the percent above. Okay, the last page, the one I was thinking about when I said maybe working backwards a little bit. No, that's this page right here. So we'll use this last page to work backwards. So here, we're going back, we're given the percentage, and we're trying to find the z-score that goes with that percentile, or percentage. So here I have a story about pizza consumption. It's totally made up, so don't pay too much attention to the numbers. Most of my numbers for my notes are made up, so hopefully not taking them for actual factual numbers. That's why there's no sources. We're just using them for examples. There's 46 slices for a mean, so the average person consumes 46 slices if you believe my made up numbers. and standard deviation of 8 slices. They want to know how many pizza slices corresponds with a 90th percentile. So we're going to have to go back and figure out the z-score and then use that to go back and figure out how many slices that equates to. So first off, 90th percentile, if I look at my chart, 90th percentile is about 90.32. So that's going to be a z-score of 1.3. From the chart, 90.32% turns into 1.3 for a z-score. So we're going to use this z-score, and then knowing the z-score, we can go back and figure out how many slices of pizza this is. We'll still use the z-score formula. We have the value minus the mean over the standard deviation. And we have most of this information. We have the z-score. We have the value, which in this case, or sorry, we have the mean, not the value. We have the mean, which is 46 slices, and the standard deviation, which is 8. So we can put that in. We have 1.3 as the z-score. We don't know the value, so I'm going to put x for the value, minus the mean, which is 46, and the standard deviation, which is 8. So I just got to go backwards and figure out what x is. Well, this is a little bit of algebra. We can undo division by multiplying, so I'll multiply both sides by 8. Now I can cancel this side. And what is 8 times 1.3? So 8 times 1.3 is 10.4. So we have 10.4 equals x minus 46. And I can get x by itself on this side by just adding 46 across. 46. Get rid of this part. And so my value is going to be 56.4. So that tells me if you eat 56.4 slices, you're going to be at the 1.3 z-score, which means you're going to be at the 90th percentile. So 56.4 slices is the number of slices you have to eat to be in the 90th percentile. So according to this data, if you eat 56 slices, you're eating more pizza than 90% of people. That's what that would tell us. So just work a little bit backwards, knowing the percentile, going back and finding the data values. First, we have to go back and find the z-score, because the chart, right? It's the chart. If we have the percentile, it's pretty easy to find the z-score, because you can just use the chart. And then once you have the z-score, you can go back and find the actual value. Okay, let's do one more. How many slices do we need to be at the 40th percentile? Same thing, first off, we're going to use that 40th percent. So in this chart, 40%, there's not an exact value for these. You have to go to the closest value. So 40.13 is closest we get. That is negative 0.25. So 40.13% is going to lead me to the negative 0.25 for my z-score. And then again, using the z-score formula, value minus mean over standard deviation, I get this. I have negative 0.25 for the z-score, 5, equals the value we're looking for, minus the mean, which we said is 46 slices, over 8 slices standard deviation. And we can solve this and go back and figure out the number of slices. Here again, I'm going to multiply by 8. By 8. Cancel this. So I get x minus 8. Minus 46, sorry. Minus 46. 8 times the negative 0.25, it's going to be negative, and a quarter of 8 is 2. So I get 2 there. I add 46 to both sides. 46. Get rid of this minus 46. So I get 44 is x. That is the data value. So if 44 slices, that's below average, you're going to be at the 40th percentile. Still eating more pizza than 40% of people, but less than the majority, less than 60%. That's 44 slices. With these, you'll notice that every time when I solve these, I end up multiplying by the standard deviation and then adding the mean. So if you have a z-score, that always works. If you have a z-score and you want to find the original value or the value that goes with that, you can just multiply it by the standard deviation and then add the mean, and that will go back and get you the value for that. Okay, so the biggest, most important thing in this section is you should be able to find a z-score, using that z-score formula. You should be able to get your z-score. You should be able to use the 68, 95, 99.7 rule. So be able to make these little charts, draw your little chart, fill in the sections, and label it and stuff. Label the mean in the middle and the standard deviations, and then find the percent. Find your z-score, and if you have the z-score, you should be able to find the percentile. because if I ask for the percentile, that's when you got to do this extra step of throwing the z-score in the chart and then finding that corresponding percentile. And then last thing we did was going backwards. If you have the percentile, go back and find the z-score, and then you'll use that to find the data value. So that's what we covered. You'll see this section has kind of the most formulas on the formula sheet, so definitely be ready for this section on the exam. As always, if you have any questions or anything, remember you can always use the Ask My Instructor button, ask me questions, shoot me emails. I'd love to help with this stuff. Hopefully it's going well, and we'll see you next time for our last section, 60.